Hello everyone, my name is Primrose Pineda. On behalf of Park System Southeast Asia, we'd like to thank you for joining us today for the first installment of our webinar series entitled What is a Good AFM? Before we begin, let me give you a quick overview of today's session. The presentation is expected to take approximately 20 to 30 minutes, which should allow us some time for our few questions at the end. Your mics have been disabled by default to give Dr. Kim an uninterrupted speaking experience. If you click the raise your hand button at the end of the talk, I can unmute your line so you could ask the question. Or if you would prefer, you may type in any questions that you have in mind using the question module on the GoToWebinar dashboard at any time during the webinar. After the conclusion of Dr. Kim's talk, we will then go back to the series of questions that we received. We'll answer them in sequence to the best of our ability. If time does not permit for all the questions, we will send follow-up email to attendees to answer those additional questions. So at this point, I would like to give a short introduction on our speaker. Dr. Kim received his Ph.D. degree in Material Science and Engineering from Nanyang Technological University in Singapore. He joined Tokyo Institute of Technology International Research Opportunities Program in 2014 and was engaged in nano-scale chemical composition analysis using Scanning Probe Microscopy or SPM. From December 2017, he started to work in Park System as the manager of Application Technology Center. He is specialized in the enhancement of nano-mechanical measurement performance for atomic force microscopy, building up an accurate and reliable environment for electrochemical measurement using scanning probe microscopy or SPM and scanning ion conductance microscopy or SICM applications development for biology. Without further ado, it is now my pleasure to introduce our speaker for this webinar, Dr. J. Kim of Park Systems. Dr. Kim, please.
Hello, everyone. My name is J. Kim, and today I'm going to talk about all about Atomic Force Microscope. Let me share my presentation. Okay. As I said, today I'm going to talk about Atomic Force Microscope. What is a good AFM? So here is today's outline. First of all, I'm going to talk about what is a good AFM, and after that, I'm going to talk about also the AFM surface imaging, the imaging mode. And after that, I'm going to present how to utilize AFM. Let's start with what is AFM. The full name of AFM is Atomic Force Microscope. As you can see the name, the AFM is a sort of microscope, and microscope is for imaging tool. And when people think about imaging, most of them told me, oh, it is from capturing, like taking a picture. However, for the imaging, we have another option, like the scanning. Of course, the capturing is quite simple and fast. It's quite good option, but using scanning, we are able to be looking at all part of the surface. And the AFM is the scanning technique. Like this, using this cantilever and very sharp tip, AFM can scan the sample surface line by line and make an image with X, Y, and G direction, X, Y, and G information. So I can say the AFM is not like just typical optical microscope, but it's like a probing lava or scanning lava. Here is some comparisons. Our eyes, naked eyes, or optical microscope, or electron microscope like a SEM or TEM. Of course, they are nice technique and they have good advantages, but regarding resolution, sample population, environment limits. The AFM can cover those kind of things. We can emit with super high resolution and almost no limit of sample variation and three-dimensional information and no limit of measurement environment. Yet this is quite versatile technique, the AFM. Here is the SPM, the Scanning Probe Microscope families. Actually, this SPM is some big meaning. So inside of SPM, AFM is in here. And start from STM, the Scanning Tunneling Microscope. AFM was invented in 1986. And after that, this kind of many sort of measurement modes were developed. And usually when people think about AFM, AFM can only take just a surface topography or surface height measurement. But inside of AFM or AFM families, we can take many kind of samples property like electrical properties, mechanical properties, thermal, magnetic, or sometimes electrochemistry and electrochemical or other properties we can measure with height information. And now I think some other new optional mode is being developed, maybe somewhere. So it is quite versatile, as I said. And next, let's go to AFM part, AFM key part. Basically, we have XY scanner in here, and G scanner is in offside of the XY scanner. And they move their own direction, like an X or Y or G direction, and collect this three-dimensional information. Then you can see the surface topography or surface morphology. And at the bottom of this G scanner, AFM cantilever is positioned, and using this laser source and PSPD, the position sensitive photodiode, we can detect the cantilever position and movement. This is a simpler version with the real pictures. And this is the cantilever. And using these lasers and meter source, we can recognize the cantilever's position. In here, this is the XY scanner, loading a sample on XY scanner, and this laser align on this cantilever and scanning with this sharp tip. Then we can get the sample surface topography. And it is just quite brief imaging procedure of AFM. For the resolution, samples properties measurement, and complicated structure, even scanning speed, this cantilever and tip is one of the most important part of the AFM. And there is quite a variety of cantilevers and tips, like different geometry and different tip cutting or different materials, properties, and so on. There are lots of cases. So if you want to measure something, if you measure your samples using AFM, you should choose quite proper cantilever and tip. Sometimes you have to choose very hard with long or short pi, or if your sample is quite soft, then you have to choose soft cantilever. Also, you should choose sharp or blunt, or sometimes high aspect ratio. Like this choice of cantilever or choice of AFM tip is quite important. Of course, if you have no idea or I don't know about this cantilever and tip, then you can contact us. Now, I think we can communicate and we can help you for the best cantilever choice or best AFM research. That is basically to help you understanding of AFM. So From here, you can monitor your sample's image, and also you can check the real-time line profile of here, this window. And once again, for the AFM imaging, loading your sample on XY scanner and position the cantilever. After that, scanning. Then you can see the morphology of your sample like this. It's not difficult, just easy, and it's quite simple. Next, let's talk about what is a good AFM. Since AFM has been developed, there are many trials to make a better performance, to make the best AFM. In conventional AFM, in conventional AFM, this X, Y, and G scanner is just all in one type, like we call the tube scanner. But this is good, but the main problem of this tube scanner is first image distortion, and also it has some slow G response. And due to this kind of all-in-one tube scanner structure, images are not flat, not perfectly flat, and also sometimes just tape wearing issues. To figure out those issues, we separate XY and G scanner. It means the XY and G scanner moves independently. It's quite a simple way, but quite powerful solution. Using this XY scanner can make a flat XY motion, and this G scanner can demonstrate a fast G servo response. And it implies we can operate true non-contact AFM. Here is a good example of true non-contact mode imaging. In here, we perform the long-time lipid measurement using just one cantilever, just one AFM tip. And as shown in these figures, from the first image to 5,000 image to 10,000 image, and finally 15,000 image, there are just constant roughness value. We can confirm very constant roughness value, and also from these images, almost same, nothing changed. Now, my previous slide, generally this surface roughness values decrease by wearing of the tip pad. Like this. Of course, start from very fresh condition, but during the scanning, after the scanning, this tip goes quite blunt, so the roughness will be decreased. But in our system, as you can see, these figures, these images, and these numbers, there is no tip wearing, and it means it's quite truly non-contact imaging. Here is the same test, but we used four AFM tips, and with the lipid imaging, from first to 800. And from these numbers, as you can see in here, tip number 1 to 4 has quite constant value, quite similar value. And it also means it's quite non-contact and there's no tip wearing. Next, we change the sample type, not a flat surface, but deep trenches with a very steep word structure. And normally this sort of sample, if a G solver response is not proper or some slow G solver response, this AFM tip will be broken very easily. However, our system show very stable performance, like from the new tip, and after taking 20 images, see this sharp shape is maintained. So this non-contact mode preserves very sharp tip shape. I can say there is no tip damage. And it's another lipid test, but it's about height measurement. We performed 100 images on 3 different days, and the result shows very constant height value in here. And it indicates our scanner, the G scanner and XY scanner performance, ideally stable and reliable. The main purpose of AFM is to investigate the surface morphology with nanoscale. So the flat surface and flat XY motion is very important to show clear feature, not an image distortion, or not not an image distortion. So to be a good AFM, the representation of flat surface or no imaging artifact is essential, with excellent linearity and orthogonality. And like this, they just separated or decoupled XY scanner shows quite flat surface without any imaging flattening process. So to sum up, what is a good AFM? Of course, you need to be able to trust your equipment, the reliability. In other words, we cannot see any structure, we cannot see anything by our eyes because that is too small, quite small. So we have no option but just trust the machine entirely. So the reliability is the first one to be a good AFM. For the reliability, repeatability or reproducibility and no imaging distortion are essential. And additionally, to be a good AFM, we should have no noise level and easy operation, automation system, and of course, no equipment trouble and fast supporting system. Fast supporting system is required. And next, I'm going to present AFM imaging mode: contact, non-contact, and tapping mode. And this slide shows some very brief process of the AFM imaging operation. I'll start from this AFM cantilever and tip position. And this tip moves down to sample surface and approaching. And approaching means the AFM tip is positioned on surface. Sometimes contact, or sometimes just on sample surface. And move G scanner up and down to maintain a constant value from the sample. And this constant value means in contact mode, just force, and non-contact mode is amplitude. And also, we just simply speaking, this constant value is interaction between tip and sample. And I think the next webinar session, the September one, I'm gonna explain one by one and more some details. And after that, the G scanner and XY scanner scan the surface, then we can see the sample's topography. For the imaging mode, for the AFM imaging mode, the contact mode is the first. But yeah, this is quite simplest way to acquire the surface image. As from the mode name, contact mode, this AFM tip physically contacts with sample surface with some specific force. And as I said, it is quite simple, but problem is that it is quite easy to damage or scratch or broken the sample surface or tip because it's physical contact. So the contact mode is generally not used for topography imaging. However, this contact mode is widely used for option modes like lateral force measurement or current, resistance, piezo response, summer, and other mechanical properties. Like using this contact mode, we can get other some sample property with height image, but not just only height image. Usually we do not use this contact mode. The non-contact mode. I think in AFM, most of I think approximately over the 90%, the non-contact mode is utilized for the imaging, height imaging. It is the most stable way to acquire the sample topography. In contact mode, the AFM tip physically contacts sample surface, but in this non-contact mode, no, there is no contact. This AFM tip is positioned over the surface with a few nanometer or tens of nanometer above the sample surface and keep a certain distance between AFM tip and sample surface. So there's no contact. And scanning. So this AFM tip never touched the sample surface, so that much less AFM tip wearing. And it is also a base method for many other option measurement, which require the distance between tip and sample. It is somewhat different from contact mode. And next is tapping mode. This tapping mode is quite similar for non-contact mode, but difference is AFM tip physically tap the sample surface. Also, I can say, oh, it's physical contact, but tap, 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 tap. So that's why the mode name is a tapping mode. The cantilever vibrates very near to the sample surface, and so it intermittently taps the sample surface. The main application of this tapping mode is that we can acquire phase image to recognize samples some properties, mechanical properties or other properties relatively. For example, we have a blended or mixed polymer sample. We can see the phase difference using this tapping mode, and we can recognize or we can determine 2 or 3 different polymers region. About the phase image, I think also I can explain about the phase image the next webinar session. And however, this tapping mode is quite good, but the problem is, anyway, this AFM tip touch or contact the sample surface. So sometimes this AFM tip very easily broken or blunted, or this sample surface can be damaged. So here is the summary of imaging mode. Using contact mode, okay, of course we can get a height image using contact mode, but it is physically contact between tip and sample. So quite easily can be tip and sample damage, scratch or broken or other things. But we can utilize this contact mode for the optional modes. Non-contact mode is very good option for height imaging. No sample or no tip damage. So most of case, you can use this non-contact mode for height imaging. Tapping mode is this intermittently tap the sample surface. So if you want to see some phase image, like some 2 or 3 different materials on one sample, you can use tapping mode and you can see some different phase signal. So you can choose some imaging mode, depends on your sample or depends on your purpose, imaging purpose. Next, let's move on to how to utilize AFM. How to utilize AFM for your research. The first thing is to investigate the surface topography. Sometimes low features, sometimes comparison between before and after some treatment. Also, AFM is a scanning technique, so we can measure quite accurate numbers like width, depth, or height, pitches, angle, and others. And next slide, let me show you some examples about AFM application, and hope it helps you for understanding how to utilize AFM for your research, for your samples. Okay, here are the very simple but very intuitive example. This last one is imaging of aluminum projected pattern with 100 by 100 micrometer. And this light one is graphene pattern with 100 nanometer by 100 nanometer. Now like this, using AFM, we can obtain surface topographical information very clearly, both micrometer and nanometer scale. Depends on your sample type. You can choose your imaging size. Then you can see your sample surface very clearly and very easily. And next, it is a good example for surface modification. From the bare titanium surface, we can investigate the changed sample surface due to acid treatment. Also, we can look into the numbers from the line profile in here like this. Before the acid treatment, roughness is about just, I think that about 100 nanometer or something. Well, anyway, this nanometer scale. But after the acid treatment, it increased. Is it 10 or 20 times increased, like just micrometer scale? Of course, like this, we can see this surface change surface using AFM. Next sample is molybdenum disulfide layers on silicon oxide. And as shown in this image, we can clearly check the height information layer by layer, even sub-nanometer scale. This from the substrate and layer 1 is around 44.5 nanometer, but this layer 1 to layer 2 is just below the 1 nanometer. So about 0.7 nanometer. So anyway, we can check this nanometer or sub-nanometer scale. And next is the pattern imaging of SLAM and LOM. And using these images, we can confirm the constant height of pattern and also constant pattern. And this one is good one, but if it has some defect or it has some failure one, we can also adopt this AFM for the failure analysis or defect detection. Well, it is not surprising that we can perform complex or complicated structure monitoring using AFM. Like this sample, like a trench acid profiling method, we can image the trench structure with this 3D image with this line profile. Micro or nanoscale, broad or steep structure, It's okay. It's not a problem. We can perform all the types using AFM. And we can also investigate some quite complex or quite complicated structure. And also we can image this trench structure and measure the critical angle with constant value. Here's the result of the lipid measurement for angle analysis. And in here, we can check this trench structure with this image, and also we can measure the angle. And this angle is shows the quite constant value. So as shown in this table, truly constant numbers we can confirm. So it's quite reliable system. And with angle measurement, we also can image this sidewall structure. Compared with the SECM, the scanning electron microscope, AFM also shows the quite similar image with these specific numbers, like angles or loftiness or the sidewall structures. So this is my last slide. As I presented, so scan accuracy and repeatability as essential factors for a good AFM. And using AFM, surface investigation on various measurement conditions are possible. And more AFM applications for a variety of research fields are currently developing. So you can use AFM, and you can use AFM to expand your research field. And Park AFM will continue to evolve into more precise and versatile and user-friendly instrument. And thank you for your attention. And if you have a question, you can talk during this webinar, or you can just email me. Then we can communicate. Thank you.
Thank you for that very informative lecture, Dr. Kim. So at this time, we will be fielding questions, from anyone. So I'll give everyone here a couple of minutes to digest the information that was presented, and we'll be handling the questions through that module here in the control panel.
And also you can see this email address. You can just email me or our team, then we can communicate and we can answer your question, or we can help you to understand about just all about the AFM.
Okay, looks like we have our first question. So here's the first question, Dr. Kim.
Yep.
So regarding the true non-contact of the Park systems, what makes it different to the usual non-contact mode measurement?
Usual what measurement? Sorry.
The usual non-contact mode measurement. I will repeat it again. Regarding the true non-contact of the Park system, what makes it different to the usual non-contact mode measurement?
Okay, yeah. So usually, so in our system, this X, Y, and G scanner is decoupled, so quite fast G-solver response we have. So it means we can make very truly non-contact. So the conventional one or other company, not a company, or other system has sometimes when they meet some complex or quite steep structure, this tip can touch very high chance to touch the surface, but our system usually do not touch even that quite complex structure. That is quite good advantage of the new designed AFM.
Okay, thank you, Dr. Kim.
Yeah.
So we have another question here. Is it possible to get elemental composition?
Elemental composition? Sorry, Primrose, the elemental composition, you mean?
Yes, Dr. Kim. The question is it possible to get elemental composition? Is it possible?
Actually, using AFM, we said this is the atomic level or nanometer scale like this, but elementary fission is somewhat different story. So you have to combine some other technique like XLD or other some like kind of that chemical composition technique. So it's my answer is a little difficult to get at.
Okay, thank you very much for
Sure.
that. So I guess that's it for now. So you can continue to type in questions as we wrap up. And if anything comes in, we will reach out to the attendees via email afterwards and answer all those questions. So thank you, Dr. Kim. And
Thank
on
you.
behalf of
Yep.
yeah, on behalf of Dr. Kim and the rest of the staff here at the technical marketing team for Park Systems, thank you all for making time amid your busy schedules to join us here today. It's been our pleasure to host this webinar, and we hope to see you again at our future webinars from Park Systems soon. Have a good day, everyone.